So it's my pleasure to introduce Charlotte KRISTJANSEN from the Niels Bohr. We give a talk on quantum quenches from quantum fields. So, Charlotte.
Okay, thank you. So let me start by thanking the organizers for setting up this conference to celebrate Emmanuel, because I think he really deserves it. I mean, Emmanuel, I always admired you for your very bright and brilliant mind, and not least your very modest way of handling it. And for me, you are always a master of combinatorics and of mathematical physics. And I tried very hard to find a problem in combinatorics I could speak about today, but I kind of left the field 25 years ago. So I chose to talk about something which is only vaguely or indirectly connected to combinatorics. Namely, I will try to explain how you can use methods from quantum field theory, more precisely the quantum field theory which enters the ADS-CFT correspondence to study quantum quenches in statistical mechanics and condensed matter physics. But at an occasion like this, one should also think a bit back and try to remember when we met for the first time. But for me, that was an easy exercise, because I did that exercise already last year when we celebrated Philippe, because I met the two of you for the first time simultaneously when I came to Saclay as a young postdoc. And yeah, I remember both of you as very welcoming, and especially with you, Emmanuel, I enjoyed many train rides to and from Paris and car rides from Le Guichet to Saclay, which you generously offered. Well, we didn't collaborate when I was here, but started only like 5 years later. And that collaboration then lasted for some years, and I went off in an orthogonal direction. But after that, we met from time to time and always had nice chats. We mostly met here in Saclay when I was visiting, but also one time Emmanuel visited Copenhagen with his wife, Celine. But yeah, unfortunately, I don't have any funny old pictures from that visit that I can show, but at least I have some pictures from a funny place that we visited during your stay, also with your wife and my husband. Namely, we went to this open air museum, which is a place where they illustrate how people lived in the Iron Ages. And they do that very lively by actually having families living there during the summer. And you can apply to become one of those families, or pay to become one of those families, rather. So we visited during a very nice summer day, and we saw both the place where the families lived and also the mysterious dark bog where sacrifices were made. And I remember Emmanuel, with his very bright and brilliant mind, he immediately spotted some objects which didn't belong to the Iron Age. There were some guys wearing glasses, and there were also some modern toys laying around. But this place still exists, and there are many other interesting places to see and visit in Denmark, so maybe you should consider a vacation in the past, or if not that, at least coming back at some point. So maybe I should come back to physics. And well, here I've shown some pictures, what I consider to be iconic images from physics, modern physics. So on the left-hand side, I have some images from theoretical high-energy physics, and on the right, some images from condensed matter or statistical physics. So here, this image, it shows the discovery of the Higgs particle at CERN. And this picture down here is not from an actual experiment, but it illustrates the concept of quark confinement, which constitutes one of the 7 millennium problems posed by the Clay Mathematical Institute. The picture over here is from a Nature paper, and it illustrates one of the first quantum quench experiments with cold atoms. In such an experiment, you set out the system in a non-equilibrium state, and you see how it develops over time. And what I want to do is to show how you can use some of the methods developed for the study of Higgs physics and quark confinement to study the development of a quantum many-body system after a sudden disturbance. Okay. So let's start in a simple way. So let's imagine we have a quantum system that it's in equilibrium, and we make a certain sudden disturbance. Then we want to investigate what happens after the disturbance. How does it equilibrate, and how does its entanglement entropy between different parts of the system develop? Another way to consider the system is to say that you have a quantum system with a certain Hamiltonian, and you set out the system in a complicated initial state, which is not a simple linear combination of eigenstates. And then you want to study the time development of the system. And here is an image from the quantum quench experiment on the previous slide, where you see how the positions of the atoms oscillate after the quench. Okay, so after such a quench, maybe you're interested in studying the time development of some local observable. That's typically what you would like to do. So in simple terms, you would want to, for instance, compute a matrix element of this type here, where psi0 is your initial state. And let's now assume that that system is described by a Hamiltonian, which is actually integrable, so that you know all its eigenvalues and eigenstates. Then you would insert a complete set of states at these 2 points and write the matrix element as this sum here. So if the state is integrable, then you would normally know these matrix elements here. And the question I want to ask is, when can you actually compute these overlaps analytically in closed form? If you can do that, you have in principle access to all the information about the system after the quench. And answering this question, it's not only relevant for studying the time development of such a quantum system after a quench, but it's actually also a problem which describes certain correlation functions in the IPhT correspondence in theoretical high energy physics. Okay, so let's take a simple example. Let's assume that our quantum system is just a simple spin chain, for instance, the Heisenberg spin chains, where the spins can point either up or down. Then a general state of the system is just an assignment of spins to all the sides in the chain. And we know for this simple spin chain all the eigenvalues and the eigenstates. And I will say that a quench is integrable if, for this particular initial state that we set the system out in, we can compute all the overlaps between the initial state and the eigenstates. And I will come back more to explaining in more precise terms what it means for me for a quench to be integrable later. But there has actually been identified a number of such integrable initial states which are relevant for ADS-CFT, and that's why they were discovered. So one type of integrable initial states are special types of matrix product states. So a matrix product state is a very general spin chain state where you sum over all spin configurations of the chain, and for each spin state at a given site, you associate a matrix. And then the coefficient of this state with the general spin assignment is just a trace of the corresponding spin, the corresponding matrices which have been assigned to the various states. So for instance, for the Heisenberg spin chain, you can associate a matrix T1 to spin up and another matrix T2 to spin down. And these matrices can have any dimension. It's known as the bond dimension in the language of tensor networks. And we're interested in finding out when can we compute in closed form the overlap between such a state and the eigenstate of the spin chain. Okay, and that's possible for certain particular matrix product states. There are other types of integrable quenches which pop up in the ADS-CFT correspondence, namely initial states in the form of so-called valence bond states or two-side product states. So they are direct two-side states with some coefficients k here. They also sometimes appear, and these two-side product states, they correspond basically to weak contractions in the field theory language. Then more recently, there's a new type of integrable initial states which have been identified in at least bosonic spin chains, and they are known as cross-cap states. There are also two-side product states, but they are states where a spin at a site J is correlated with a spin at the opposite, or the diametrically opposite side of the chain, if you consider the chain to be periodic. These boundary states have turned out also to be integrable, although their importance in the ADS-CFT correspondence has not really been understood yet. They're probably related to string theories or non-orientable manifolds, or gauge theories with orthogonal or gauge groups. Okay. So let's see where these various initial states come into the game in the ADS-CFT correspondence. Sorry. Okay, so the ADS-CFT correspondence, it's a duality between quantum field theory on one side and string theory on another side. And to illustrate the importance of this duality for the development of high energy physics, I can mention that the original paper by Maldacena now has more than 25,000 citations, so it's something which has had a lot of impact. But what has been of interest for me is that the common spectrum of these two theories, the quantum field theory and the string theory, has been mapped onto the spectrum of a much simpler system, namely a quantum many-body system in the form of a spin chain. So what I will be speaking about, or what I am speaking about today, is something which relates to this left part of the diagram, and it has nothing to do with the string theory for the moment, at least. Okay, so just a few more words about this duality for those of you who don't work with it. So the key idea in this duality is actually that of an excitation. So we all learned in quantum field theory that a particle is an excitation of a field, and in the same way, in string theory, one describes a string as something which has to do with excitations. More precisely, a string is a two-dimensional worldsheet which has excitations on it. And in a spin chain, you typically also describe the eigenstates as states with some excitations on top of a vacuum. And the idea of this entire duality is that you map the excitations in the field theory to the excitations in the string theory, and you map both of them to the excitations on a spin chain. And it turns out that the spin chain that you need is completely determined by the symmetries, so that the interactions between these excitations are also completely determined by symmetries. And the kind of spin chain you need is a super spin chain, having some super Lie algebra symmetry, and having not only one type of excitations like the Heisenberg spin chain, but 16 different types of excitations, which can be both bosonic and fermionic. And that spin chain, which appears, actually turns out to be integrable and exactly solvable. And you can consider the spin chain, or the spin chain picture perturbatively. Then the range of the spin chain interaction will be L+1 if you're working at loop order L in the field theory. But the spin chain can actually be defined also non-perturbatively, if you like. Okay. So once again, this ADS-CFT duality, it comes with a dictionary which translates quantities in the quantum field theory to quantities in the spin chain. And now, in recent years, it's been an active topic to try and introduce defects in quantum field theories. And defects are, of course, important because, well, all realistic systems have defects or impurities, and in theoretical high energy physics, we also use defects to break symmetries. For instance, supersymmetry, which we have not observed in the real world, but that we often work with. But now it turns out that the process of introducing a defect in the field theory actually corresponds to performing a quench in the underlying spin chain. So more precisely, introducing a defect corresponds to setting out the spin chain in an initial state, which is not an eigenstate of the system. Okay. Okay, so here's a little bit more precisely the same story. So what the duality does, well, first of all, the quantum field theory which enters the duality is a conformal field theory, and one should work with its good conformal operators. So the duality, it maps the good conformal operators in the field theory to the string states in the string theory, and at the same time maps both to the eigenstates of an integrable superspin chain. And there are several examples of this duality. The main one is one where the field theory lives in 4 dimensions, and that field theory is called n equals 4 super young Mills. There's a very similar story where the field theory lives in 3 dimensions, and that's called ABGM theory. And there are also examples in lower dimensions, but they are not as well understood and are not really connected to spin chains. And everything that I will speak about which relates to spin chain always is the planar or large n limit of the field theories, which are non-abelian gauge theories. Okay, so this is a pure ADS-CFT correspondence. Now I want to introduce a defect in the field theory, and I choose some flat defect of some dimension or some codimension d. In the string theory picture, it corresponds to inserting some probe brain, some higher dimensional membrane which lives in the string theory background and where strings can end. In the spin chain picture, it corresponds to introducing some boundary state, the state that I denoted as psi 0 before, and then the overlap between psi 0 and an eigenstate of the spin chain is actually a correlation function in my quantum field theory, and it will typically be a one-point function, and I will explain exactly how. And I'm interested in understanding when this system where I've introduced a defect is still integrable, and I can compute this overlap exactly. Okay, so let me explain you how an initial state in the form of a matrix product state appears in this picture. So in my ADS-CFT correspondence, I have my field theory, which is, as I said, called n equals 4 super young Mills theory. And in that 4-dimensional theory, I want to introduce a 3-dimensional defect. And that defect should separate 2 regions of space-time where the rank of the gauge group is different. And the way I implement this is by assigning a non-vanishing vacuum expectation value to some of the scalar fields, some Higgs fields, on one side, but not on the other. And this difference in the rank of the gauge group, K, is actually what becomes the bond dimension of my matrix product states, as you will see in the next slide. So in my particular field theory, I actually have 4 scalar fields, and the nicest way to assign vacuum expectations values to them is to assign non-vanishing values to 3 of the fields and vanishing to 3 of the others. But I cannot take any Beths, of course, so they have to fulfill the equations of motions of the field theory, and that equation of motion involves some quartic interaction between the fields, and that interaction term, it actually tells me that fields of this type here, where I put a non-vanishing matrix in the upper left-hand corner, which fulfills the SU2 commutation relations, are good vacuum expectation values. So I can put up here a matrix, which is I have 3 non-vanishing matrices, and they can be chosen to be the generators of SU2 in some representation of any dimension k, irreducible, preferably. Okay, and then to keep the quantum field theory conformal, I should also let this vacuum expectation value depend on the distance from the defect. That's the right scaling to keep conformal symmetry. Okay, so now I'm interested in computing one-point functions in this defect quantum field theory. It's the simplest thing you can compute, and the form of one-point functions are fixed by conformal invariance. They're bound to take this form here, where x3 is the distance to the defect and c is some structure constant that you have to compute. But to actually find the good conformal operators for which I can compute the one-point functions, I have to solve a combinatorial problem. Because my good conformal operators are in general some complicated linear combination of single trace operators. But the problem of finding the good conformal operators was solved very elegantly by Minahan and Sorembo, who found out that the good conformal operators could be identified with the eigenstates of an integrable SO6 spin chain. So you simply map the 6 scalar fields onto the 6 possible states of an SO6 spin chain. And then the eigenstates of the spin chain gives you the good conformal operators. So if you have an eigenstate of the spin chain, you can find your corresponding good conformal operator. Okay? And if I want to find the one-point function of such an operator at leading order, I should simply take my good conformal operator and insert the non-vanishing vacuum expectation values for the 6 fields. So this is what I've written here. I replace the phi's by these matrices that I call Ti. And this is where the concept of a matrix product state comes in handy, because I can formulate the computation of this one-point function very neatly if I introduce this matrix product state here, where again I sum over all spin configurations. I associate to each spin state the corresponding vacuum expectation value, which in half of the cases will be 0. And then my one-point function can simply be formulated as the overlap between this matrix product state and the beta eigenstate corresponding to the good conformal operator. Because what this matrix product state does is that it picks out the part of the eigenstate which has the same combination of spins, and then it replaces it with this trace of the corresponding representation matrices. So what we have to compute is simply this overlap, and then to normalize correctly, we have to divide by this length of the norm of the beta eigenstate. Okay. And now the question I wanted to ask was, when can I actually compute this exactly? And now we can get some help from our friends from the 90s, because it was already understood by then when you can have an integrable boundary in a continuous quantum field theory. And a boundary is integrable, which if you can have at that boundary only reflection and no production or annihilation of particles. So you can have that particles change their momenta from p to minus p, and they can also exchange some internal quantum numbers, but particle production and annihilation is forbidden. Then one also has to have that the scattering in the bulk of the field theory has to be compatible with the reflection at the boundary, so that a particle, you have the same amplitude whether a particle 1 reflects from the boundary before it scatters with particle 2 or vice versa. And that's the information which is contained in the so-called boundary Yang-Baxter equation for the reflection matrix. But you can also, instead of looking at a boundary in space, as I did here, you can do a weak rotation and look at a boundary in time. And then this integrability condition, it translates into the condition that your initial state, your boundary, must be a state which is built from a coherent superposition of excitations with momenta plus and minus p. And then, of course, there's also some analog of the boundary Yang-Baxter equation for initial states. But especially this formulation over here is something that you can very easily translate to a spin chain. And to explain that, let's go back to the Heisenberg spin chain. So let's say that we take the vacuum state to be the state with all spins down. Then you can consider, if you consider an excited state, an eigenstate with m spins pointing up, then it's described in terms of a number of Bethe roots or Bethe momenta, which have to fulfill a number of Bethe equations. And this system is known to be an integrable system, and it means that it has a number of conserved charges which commute with each other and with the Hamiltonian. And now you can organize these charges so that half of them are odd under parity and the other half are even. And if you do that, then it's very simple to write down a condition for the fact that your initial state has to be a superposition of excitations with momenta plus or minus p, because that will only happen if it's killed by all the odd charges. So an integrable initial state must at least be one which is killed by all the odd charges of the spin chain. That you can also formulate in a general way if you introduce a transfer matrix, which is the generating function for all the charges. Then you get a relation like this, which is the transfer matrix, and pi is a parity operation, space-time parity. And now you see, with this condition here, you have a very explicit way in which you can check whether you can expect an initial state to be integrable or not. Because these charges, they are known in closed form. The transfer matrices are known in closed form for integrable spin chains. Okay. Working in IPhT-TV, we are of course looking for a specific kind of initial states, and we have identified a number which are actually integrable, and we have also found the overlap in closed form for all those cases. So there are a number of field theory defects. There are some which correspond to domain wall defects, and there's also one which corresponds to a line defect generated by a monopole living in the quantum field theory. And there are also some surface defects. They have an interpretation in the string theory side as various probranes, that's some various membranes living in the string theory background. And basically all the possible types of membranes you can have appear and can appear in some integrable configuration. So the matrix product states which appear in this as initial states, they can, like I showed before, they can contain SU2 representation matrices, and there's another case where they contain SU5 representation matrices. They can also just be diagonal matrices where you have more like a projection operator. But all of these cases, there are some nice closed formulas for the overlap. Okay, so let me try to show you what these overlap formulas look like. And to do that, I have to introduce some elements of the language of spin chain integrability. So I said already that eigenstates of a spin chain, like the Heisenberg spin chain, can be described in terms of some momenta. If you have m excitations, that is m flip spins, then you have a state characterized by m momenta, p1 to pm, or rapidities, which are defined like that. And these momenta or rapidities have to fulfill some Bethe equations, which I write like that. And meaning that if you have a solution of your Bethe equations, then you have a good conformal operator. And a specific solution of the Bethe equations you can encode in a Baxter polynomial, which is simply the simplest polynomial which have these Bethe roots as zeros. And for a given solution of the Bethe equations, you can also write down what your eigenstate is and what the corresponding operator is. And that, of course, again, is expressible entirely in terms of these Bethe roots. And in particular, the norm of the eigenstate is given in terms of the determinant of a specific matrix, which is also expressible just in terms of Bethe roots. And that matrix is a matrix you get by differentiating the exponent appearing here on the right-hand side of the Bethe equations with respect to the roots. And then to get the norm, you must take its determinant. Okay, but it's a nice closed expression, which also has its roots here at Saclay, I think. Good. Okay, and all this can be generalized to more complicated spin chains. I spoke just about the Heisenberg spin chain, but to describe the entire ADS-CFT correspondence, we need an integrable super spin chain. So you can write down the solution of an integrable spin chain of any built on any super Lie algebra symmetry of this type here. You just need the Cartan matrix and the Dynkin labels. Then the Bethe equations are given. And there is a set of Bethe equations whose number is equal to the number of nodes in the Dynkin diagram. And then you have several Baxter polynomials. You have one for each node in the Dynkin diagram of your Lie algebra. And of course, again, you have a Godin matrix, but it's just much bigger. You have to include all the roots at all the nodes of the Dynkin diagram. But the construction is the same. Oops. Okay, so yes, so now I'll try to explain the elements that will enter my overlap formulas. So the main elements are the Baxter polynomials and the Godin matrix. Okay, so here are some examples of overlaps which you can derive analytically. These are quite simple overlaps where you use an initial state which we call a delta state, which is the two-side product states of where the two neighboring sides have the same spin configuration. And those you can actually derive by taking the large length limit of the spin chain. But you see that for the Heisenberg spin chain, then the overlap, I have actually put here the overlap squared, not to have a lot of square roots. Actually, I think I'm missing one slide here because what enters these overlaps formulas are Baxter polynomials and then something which we call the superdeterminant of the Godin matrix. I think I'm missing a slide. Strange. Here, okay. Because as I said, we defined an integrable initial state as one which was annihilated by all the odd charges. And for such a state, you can easily prove that a Bethe state you have an overlap with such a state if its Bethe roots are paired. And that you simply do by sandwiching these odd charges between the initial state and the Bethe eigenstate. So in order to have a non-vanishing overlap, the Bethe roots have to be paired. When the Bethe roots are paired, the Godin matrix has a block structure because the roots are identical in pairs, and its determinant factorizes. So you can rewrite it as a determinant of an upper triangular matrix, basically, or an upper block matrix, and then you have a factorization of the determinant into two determinants. And that can actually be interpreted as a superdeterminant of the Godin matrix if you take this pairing of roots as a set 2 grading. And what enters always the overlap formulas is the ratio between this one part of the determinant and the other, and also known as the superdeterminant of the Godin matrix. Okay, and here was the first overlap formula that I also had on the slide. I showed a bit too early. The overlap with the delta state is simply given by a ratio of two Baxter polynomials, and then the superdeterminant of the Godin matrix. And that formula, it generalizes to integrable spin chains based on super Lie algebras. For instance, if you take, this is still not a super Lie algebra, it's just a SO6 spin chain. If you take an initial state, which is a delta state, so a two-side product state where the neighbors and spins are the same, then the overlap formula looks like this. You see you have now 3 Baxter polynomials, one for each node in the Dynkin diagram, and they appear in some order here in a rational combination, and then they have this superdeterminant of the Godin matrix. So that is very pretty, and you can continue and ask what is this overlap formula for the entire ADS-CFT correspondence, which is built on this one supergroup, which is known as PSU 2,2/4, which is a super Lie algebra with 7 nodes in the Dynkin diagram, some bosonic and some fermionic. And we can write down a completely closed expression for the overlap. And you see all the 7 Baxter polynomials appear in some way. And I should stress that this is an expression which is valid for any conformal operator in this theory, any length, any number of excitations, anything you can think of. Okay. So this was actually all for these delta states, which are two-side product states of identical neighbors. But eventually we want to go to these matrix product states that I started by introducing. And in that case, the overlap formula becomes a bit more complicated. It still involves the superdeterminant of the Godin matrix and some rational combination of Baxter polynomials. And the way in which to derive this formula is to find a relation between this delta function, which was a two-side product state, and then the matrix product state. And you can show that you can always do that. You can write the matrix product state as some transfer matrix with the auxiliary space in a lower dimensional representation, and then acting on this delta state. So it requires some work, but there is a systematic procedure for doing so. And once you have this expression here, you can just take the inner product with the beta eigenstates, and then you get the exact expression for the overlap. Okay, I understand I have only 1 minute left. 4 minutes left, okay. Yes, this is a procedure which has to be repeated every time you take a new representation of your super Lie algebra. But there is a more general condition which was derived recently by Thomas Gumborg. Yeah, okay, as usual, when you try to scratch the surface a little bit, things become a little bit more complicated, because the transfer matrix can sometimes factorize, and then you can have two different ways of satisfying this relation with the charges. And you can also have a generalized pairing where it's not the beta roots at a particular node which is paired, but it can be beta roots from different nodes which are paired. But there is some nice group theoretical classification which allows you to tell when an overlap is paired and when it's not paired in one way or paired in another way. But I don't have the time to go into that. There's also a nice systematic way to find the overlap in a closed form. So what you have to do is to solve something called the KT relation, where you look for a sort of reflection matrix K, which has both bulk indices like the transfer matrix and boundary indices like the matrix product state has if you cut it open. And if you find such a matrix, then there's also a specific recursive procedure from which you can extract the overlap formula. And these overlap formulas always have the same structure. They involve the superdeterminant of the Godin matrix, which of course is different in each case because this is expressed in terms of all the roots of your solution. And then there's a prefactor which involves only Baxter polynomials, or more precisely, mostly square roots of Baxter polynomials. And there's a sum from 1 up to the bond dimension of the matrix product state. So I should stress that these formulas like this, they encode a lot of information. It's all operators of your entire theory, any length, any number of excitations, and so on. Everything is included here, is expressed just in terms of the Bethe solution of the Bethe equations. Okay, maybe I should finish here. So what have we learned from all this? Well, we have found a precise definition of what it means to have an integrable quench, and we have devised a concrete method to test whether a quench is integrable or not. And then we have found all these overlap formulas in closed form, and in principle they contain all the information there is about the post-quench behavior of our quantum system. And what can we hope to learn? Well, what I think we can hope to get from this is some novel universality classes of post-quench behavior, because coming from theoretical high-energy physics, we have some spin chains which lie completely outside the realm of condensed matter and statistical physics. We have spin chains which have an enormous amount of excitations and a high degree of nesting. They are in general long range, and they can even be length changing. And then we have also provided condensed matter and statistical mechanics with some new types of quench initial states, namely these matrix product states that did not really appear to be relevant before, and these cross-cap states which have an interesting type of entanglement. Okay, thank you.
So we have 5 minutes for questions. Thank you. Thank you, Charlotte, for being perfect in time. And so we have time for questions. Yes? I'm not sure. I'm very good at... Huh?
I could speak loudly. So imagine I introduce some defect in the theory. And the defect has some quantum numbers, right? So as you said, you could introduce some Wilson loop operators, etc. Imagine I go to the limit when this operator is infinitely heavy.
Yeah.
So you have a formula which will predict me, so those overlap which you computed with some function of the parameters of the operator.
Yeah.
But then physically I know that if I go to the limit when the operator becomes infinitely heavy, this operator could destabilize the theory. What I mean, it could introduce some instability. So therefore, your formula should have some singularity built in as a function of quantum numbers of the operators. Where the singularity comes from, and could you say something more about those instabilities?
I think in the language of string theory, I always work in the probe approximation, where the probe does not disturb the background. So my background is always ADS5 times S5, and I think this somehow also reveals itself on the field theory side, that there's a restricted set of defects that I can actually treat in this way. And also, it is the defects that I can honestly treat are defects which are of holonomic type, where the defect is defined by the divergence of some fields, which have some vacuum expectation values.
But do you agree that there should be back reaction? So
yes.
what you're saying, you're just thinking about like perturbation theory. Let's say you introduce some defect in your theory and you're expecting the defect doesn't have back reaction on the theory itself.
Yes.
But I'm saying once you have exact formula, I may try to push this formula to the limit when back reaction is very strong.
That's true.
Which is the formula is exact, it should know about this. So
That
my question is, how does your formula knows about this?
That is true. There are only a few of these defects where there's actually, so far, a conjecture for an all-loop result. And there one would, in principle, be able to answer your question. But it has not been attempted. But I agree, it would be interesting. Yeah.
Okay. One more question from here.
Do you know if there is a link between the factorization of the Godin determinant that you mentioned and the Wiener-Hopf factorization?
I think you have to remind me of the Wiener-Hopf factorization. Maybe we can discuss it afterwards.
Yeah, or if anyone's known in the room, I will be interested in this.
Yeah.
Still 2 minutes for question. Oh,
okay.
So, feel free. Don't be shy. You can throw it. Question? No? Maybe, well, just one. You spoke about various universality classes of quenches. Can you say a word about it? For instance, does it correspond in your different models of different kind of symmetry or supersymmetry?
This with the different universality classes, that is my dream project. I would really like to study how the post-quench behavior is for various types of spin chains and various types of initial states. So I was hoping that you could study the time development of some observable, some kind of maybe some entanglement entropy of different kinds of subsystems, and then find some scaling exponents which are different for different models and so on. But it's still a dream project I have not
Thank you.
managed.
So, okay, well, let us thank Charlotte again.